introduction you share there is quite nice. I do, however, have to say we record this for the YouTube channel, right? As we mentioned, that means I would usually start a little bit with why this is at all relevant for RAISE, why transformers might be interesting for RAISE, talking a bit about RAISE. And then, as I also said to you, I would cover a little bit the idea of, going the major footsteps from AI to transformers, which is quite a big one, covering a little bit the ideas of, RNNs and LSTMs, shortages of this, but then really stop at transformer models and for you, but also do some CNNs just at the basis, just that the people relate to the difference between basically one image at once or sequence models and so on, so that you can really go medias and res, as you would say. But still, I think it's good for the YouTube channel and for our projects and others to show that a little bit, because they are not all AI hardcore people, right? They are mostly physicists in simulation sciences. Some are data experts, but not necessarily all AI experts. That's why I do some intro. At the end, we have also some Q&A. So basically, there should be also time enough for that. We would have roughly an hour, but we are a bit flexible in that, right? So let's see. Good, but do you want to screen share test shortly, maybe, before we start the recording and everything?
I think after 2 years, this will hopefully work, but we can double check.
Yeah, it's maybe also the rights. Katrin, did you give the rights to Christian to share?
Yes,
that's also an important one. Okay.
Yeah.
Yeah, very good, very good. Thank you.
1 second.
Otherwise, our media expert has too much to cut and to work on and massaging the video for YouTube. So it's good maybe to just check that before.
All right.
But that looks very good. Cool.
All right.
All right. Then let's go a little bit. So the intro might be a bit interesting for you, while some aspects, of course, are boring, but I hope I keep it relatively short basically to some degree. Katrin, do we have the recording running already? Or
yes.
Okay, good. Then I think we should get started. So, up. All right, so welcome everyone to our RAISE CoE training. Today we have the interesting topic and very hot topic, transformer models. So welcome you here also in the name of our National Competence Center for HPC and AI in Iceland that is basically co-organizing this training together with the RAISE project. The idea of the agenda today is that I give you a very short intro as usual. Why is basically this topic somewhat relevant in CoE RAISE? What is the Center of Excellence about? What we're doing there? And then I will give you a very, let's say, short introduction to transformer models, which is really much more an idea of machine learning basics combined with the relevance of HPC, perhaps going a long way from image recognition techniques or machine learning for image at once to sequence models where transformer models really point. So basically, we will discuss a little bit recurrent neural networks, the shortage, the problems in that, before we then come to transformer models, where really Christian is the expert that we have here on the call. And let me just introduce the speaker a little bit. I think he can also, of course, do that later a bit more, let's say, elaborate. He is really a key expert, basically in representation learning in a group about computer graphics, doing machine learning, very different approaches, you would say, we did maybe 20 years ago in this. So basically using machine learning, deep learning. There's a small bias, I think, to earth science applications, Christian. That's what I basically got from you. But in general, you're basically having lots of methods in this Institute for Simulation and Graphics at the University of Magdeburg in Germany, where basically Christian have his group. Just shortly for me, I'm teaching high-performance computing and parallel and scalable machine learning here in the University of Iceland, but I'm also almost 20 years now in the Jülich Supercomputing Center, building that up for a long time. And also here in Iceland, I'm the EuroHPC Joint Undertaking Governing Board member. This is also quite nice to have some interesting perspectives. And I think from the governing board perspective, I can really say AI is definitely an interesting part the RAISE CoE is also a very unique center of excellence among others, what you will hear today, which is basically not directly focused on domain sciences, but really on AI at scale. Just to the University of Iceland, very briefly, the National Competence Center that we have here is structured in simulation and data labs that we built collaboratively, indeed, with the Jülich Supercomputing Center to have strong links there between the different, let's say, German labs and the Icelandic labs, with lots of different PhD students going back and forth. And the University of Iceland is quite, the largest one in the country. Basically, we don't have many universities here in Iceland. That's not surprising, but it's really the university where HPC plays a big role. Other universities have also some players, but basically HPC is hosted in the University of Iceland, and hence we are also basically representing the NCC of Iceland in the realm of the EuroHPC project, which is also co-organizing this event. And when you think about what's the strategic cooperation towards Exascale, as some of you know, the Center of Excellences are a little bit focused on the idea of moving towards Exascale in the future. There we basically, from Iceland, teaming up with the Jülich Supercomputing Center on the one hand. As you know, we will get an Exascale system probably in 2024. I think here this timeline 2023 is perhaps a little bit too aggressive. I would rather correct this to 2024 with Jupiter. But the general idea we basically created along the way with the DEEP project was modular supercomputing. I will explain later a little bit. And Iceland is also part of the LUMI, which is basically a supercomputing, the queen of the north, with 10 different countries basically paying for it. But also the idea, when you look into the heart of LUMI systems architecture, is quite modular. So you will find a LUMI G partition with GPUs, which is relevant, of course, for machine learning. Still, interesting enough, it's not based on NVIDIA. So we have also more and more heterogeneity, where also this RAISE CoE is actually working a lot in and having an interesting idea of a unique AI framework that I will explain a little bit later. So much for the welcome. Let us go a little bit to the role, why we basically do this now, a transformer model training in CoE RAISE, and basically including a little bit what is RAISE really all about. So we have here a Center of Excellence, and of course we have a web page where you find out much more information and news and our social media links. But then you look on RAISE from 10,000 feet perspective compared to other Center of Excellences, this is really the one for artificial intelligence at scale. So thinking about all the different packages you have from PyTorch, DDG, Horovod, TensorFlow, up to really low-level parts of modules at different supercomputers that needs to be basically supported if you do AI at scale. We're looking also in the scaling inherently, so the problem of batch sizes, the problem of efficiency of GPUs when you scale up, and I will explain that a little bit. But yeah, the website is there for you for more information. The general motivational approach, if you know a little bit about HPC communities, where of course, to start as simulation sciences. So we have different, let's say 5 different use cases on board, which are much more rather based on basically numerical laws, based on known laws of physics, numerical methods, which are traditionally the main use of HPC, you would say, but this has dramatically changed in the realm of the last, let's say 5 to 10 years, where deep learning really was aggressively using more and more GPUs. And of course, at the same time, we have also observed that more and more GPUs are available to the scientific community. And with this, that's also very beautiful for AI researchers, not only for training in a distributed manner, so distributed deep learning, for instance, but also for hyperparameter optimization. When you think about that, this is very costly if you're very search space of how you tune your different deep learning networks. There we can basically provide a big difference. What also is RAISE doing? I have some noise in the line. I would ask everyone please to mute. Thank you very much. But here again, the idea of RAISE is then to pursue different angles to this. We will probably in the October event hear more about surrogate modeling. So that means you basically exchange a computational costly, let's say, physical model, like for instance, here you see a CFD model of drag reduction and so on, with a maybe easier to compute surrogate model that you of course have to first train, that you basically have to scale up to the domain that you want to simulate. So this is just one example. Of course, we have many different aspects in RAISE. Hyperparameter tuning was another one that really can fill easily an exascale machine if you have high, let's say, big, large deep learning networks. So when we think about the CoE RAISE and the ideas, what we do is, of course, firstly, orient ourselves to sciences. You see, basically, we have the different types of use cases here. We have 5 different ones, which, as I said earlier, were mostly based on, let's say, numerical methods based on known physical laws and so on. And basically, you see another part of the use cases, which are much more data-driven. So first and foremost, many of you know the CERN Large Hadron Collider, which is here on board, but we have also 3D printing as a very interesting new technology, and looking what we can learn from these basically more manufacturing and really, let's say, data-intensive approaches that are not directly, of course, indirectly somehow related to physics, but not directly as simulation sciences per se. Also, for all of these, you have, of course, more information on the website. But for us, it's really relevant to see, and that brings the CoE RAISE now to play. What are the AI models which are relevant for all of these different use cases? And on top of it, what are now the frameworks? What are the approaches really used in all of that? And that brings us a little bit to transformers, where we, over time, of course, adopted in different of these use cases AI models, which is these interesting aspects. And we gathered more and more data, create data. In some occasions, like here is the sound engineering, we first have to create some data sets. But of course, here the idea is, can we learn something from all of these different use cases if there's, let's say, a more general approach in terms of the packages that we have? Of course, the AI approach in all of them will be very unique for all use cases, but then can we maybe share the know-how and the knowledge of basically adopting some AI model, let's say transformers, as we will basically learn today, with other use cases, at least of thinking about we have a similar sequence or so. So this is the idea of the CoE RAISE project, and we have different work packages there, which is a little bit basically now showing the structure of the project, not so relevant to you, just thinking about what we terms do in work package 2, which is a little bit here, the idea of the data and AI-centric one. We really scaling up machine learning codes, thinking about what are now the new frameworks bringing to us, like DeepSpeed. Some of you maybe have already heard. That's a new framework compared to rather TensorFlow, Horovod, and PyTorch in the past. So we have there already some experiments, but we're also looking into more new cutting-edge AI methods. We have adopted partly long short-term memory, but as we basically designed to learn today, the basically transformer models have even something to add on top of the idea of this long short-term memory, as we would learn later. And this goes on and go on. I think it's clear to say that with the heterogeneity in HPC, it's also relevant to benchmark this on different architectures we have in HPC. So it's not at all that simple that you deploy TensorFlow on all the different systems and it will run the same way all the time. There's really huge differences in the architectures of the systems, in the way how they configured, how they basically have access to the systems, like for instance, using Jupyter Notebook versus batch and so forth. And then one key theme that we also pursue right now is basically hyperparameter tuning. In the subsequent timeline of the project, we also move more towards the direction of neural architecture search, which is perhaps a bit more bolder, thinking about can we learn the whole architecture of a neural network, of a deep learning architecture, perhaps. So summarizing this a little bit, what we do is quite basically best expressed when you have essentially this interesting light bulb, where we have definitively lots of different hardware infrastructures, where we don't stop at conventional ones. We have also graph core with an intelligence processing unit, basically more graph-based system. We already have our baby steps taken in adopting quantum computing. For instance, quantum annealing for optimization in machine learning can be quite nicely used. And we have there already, let's say, some interesting aspects, how this really can benefit AI. Then, of course, the software jungle, as you would say, right? The software tools, there are a lot of them out there, Heat, Horovod, etc., TensorFlow, how that all fits together. And of course, orthogonal to this goes the different versions that exist. So some versions in Python just work together with these versions of TensorFlow and Horovod on these different modules on the HPC machine. So it's a very complex material, especially for those that say are not inclined in HPC before, that perhaps running just Anaconda with scikit-learn or so, and then suddenly have to, want to use HPC system, want to scale to 1,000 or 2,000 GPUs, and suddenly have a big jungle of basically systems, but also a big, let's say, heterogeneity of software there to play with. And in order to understand what systems basically we can use with what technologies is the idea of this so-called unique AI framework that we co-design essentially with the concrete use cases we have seen. This is important to really be bottom-up focused so that we don't create a high-level framework that in the end nobody will use, right? So here the idea is really learning bottom-up from use cases within RAISE. And of course, it's part of the second part of the project. Basically, we also go extending this to use case partners outside of the RAISE project. Like for instance, in medicine, we have already adopted some parts of the unique AI framework. So this is an important part. And I'll show you very soon what that really means in terms of a framework. You would be asking yourself now, is this another TensorFlow or another, Horowat? Please, please not. The community has its own tools, not yet another one. So just before we do this, a little bit the methodology, which proved quite useful in the AI RAISE, let's say, journey was really looking first at fact sheets. They are available if you want to look at them, showing a little bit like 10,000 feet perspective for each of these different use cases. What are the components relevant? What are basically the approaches that are done in these different use cases? And of course, it's true also for the data-driven use cases. All of these use cases are in one respect very unique, but also, of course, in another respect, share some common approaches, some common technologies. Then we take these common technologies, we benchmark them, we analyze them with different, let's say, data sets. Sometimes, of course, first we start with ImageNet, we start with CFAR, MNIST, and so on, before we then go to more cutting edge ones, which are really in the use cases. From there, we adopted then something called the interaction room. There's actually a training in YouTube also about the interaction room concept, where we really have different canvases, talking with the application scientists and with the HPC experts and with the AI experts together. So quite interesting, so to speak, crowd, really in context of the different use cases, but also then, in really low level, what could be potential approaches? What can we maybe learn from other use cases that already adopted some particular AI technology or some AI model, right? And this is actually also one of the motivations why we came now to a transformer training, because in the end, we discussed this in the interaction rooms that actually this might be a model we potentially could adopt. Basically, some of the use cases already started a little bit going into this direction, but we really are at the very beginning. So it's very good to have this training, I guess, now at that point in time. And if you want to learn more about basically CoE RAISE as a whole, not only the interaction room, that is here one example, please follow us on YouTube. Here goes the advertising for our social media. We can really, like more YouTube followers here. That is a good, let's say, metric that the commission likes, of course, when the people really looking, but also following our channel. So please take the time, have a look, and follow us on YouTube. Coming back a little bit to substance, what we do now in the AI software framework, and what is a little bit the output of RAISE. Of course, there's output in the different use cases in terms of sciences, how they adopt the AI models. But what we give to the community is something we call the unique AI software framework, which was recently also basically approved as an approach by our reviewers. So we basically adjust our midterm review and the whole approach that we presented, of course, in much more detail as I can present today, to not draw away the attention to transformers. Away from transformers is really this stack of tools that you see here. And there is a complete training on this AI software framework from last month. So I would also refer here a lot to the YouTube channel. But long story short is essentially making AI a little bit more easier to adopt. So you would have Jupyter Notebook scripts, which already have the right kernels for adopting them on different, let's say, HPC systems. Here you would see, especially when you think about different modules, using them then with batch system or so. Here, PhDs and different researchers, we have found out they really lose 2 to 3 days a month just really configuring the right module setup for all the different HPC systems. And this is something that we, for instance, address with basically providing a JavaScript generator that is already tuned to the different your HPC systems. And we're working on this, starting, of course, in the moment with the more Jülich system and then the Barcelona system. But the vision is really that we work together with your HPC hosting sites to have this available for many of these systems. And there is something what you don't really have to do anymore in thinking about which different modules and which different versions I really have to adopt. Here, there's lots of automatism that could help a little bit. And we regularly check then these model setups that you basically also can be sure they work. Orthogonal to this, as I was alluding earlier, we have a couple of tasks really looking into the different technologies, what we can recommend. For instance, here you see in the moment, we really recommend TensorFlow together with Horobot and then PyTorch in the, basically DDG area. They really would scale up. And of course, there are some inherent aspects in the AI that we have to think about, especially if you grow up with a number of GPUs. But we're still already looking into deep speed, which could be another, let's say, framework we recommend here as a RAISE framework. But it's something what we first have to benchmark, what we have to understand, port to different HPC systems. So this is also one part of the framework to really know how it fit it actually to different HPC environments and so forth. You see also it's not a static process. So basically, once done, we have the framework done, we always have new tools. One is, of course, now the shift from Singularity to Obtainer. Another one is adopting hyperparameter tuning with, for instance, RayTune we can recommend here. We have used this incredibly often now in many different use cases. And with the power of HPC, you're not limited, of course, in the search space. So in this sense, you can really adapt that at scale. And with this have really something to offer, which in almost all cases has something to offer for all AI models, right? Because we all share the same problem as AI people. We need to find the right set of hyperparameter, which are, of course, an application dependent and also model dependent. So this is another interesting aspect of the RAISE framework where we share how you use RayTune, how you basically adopt that easily. And then, of course, also thinking about the different HPC systems again. There are different other ways what we plan to provide, like Python APIs to make that JavaScript generator, of course, also accessible as a more API version. But I think I would refer here rather to the training we had last time to not spend too much time here talking just on basically CoE RAISE. We want to go to transformers. And I think this is something I leave here on the table for you as an interesting topic. Today, you see here what we do in all the different use cases, how they adopt all the different AI models. And we see already, interestingly enough, that the recurrent neural network structures, I will talk a little bit in my next talk, LSTMs and gated recurrent units here have been already adopted. So here is also the question, could transformers may be used? And then other use cases have already very specific ideas which transformer models could be interesting. We see that here a little bit in the 3D printing case, where you basically can consider that many of those are sequences of pictures, right? How a 3D printer is printing. And with this, you have a sequence, let's say a video in the end of pictures, where transformer models also have some role to play. So very interesting new technology that we're now adopting in RAISE and want to learn about. That's why we also are very grateful to have Christian here on board telling us more about this complex technology. However, before Christian starts, and I know you're probably waiting for him, I just want to share a little bit some, let's say, context of this. Transformers are not the easiest topic to digest, especially for our YouTube watchers that are not, let's say, have a very strong background in AI. On top of that, we have the role of HPC, where actually transformer models also are quite beneficial. I will explain that a little bit. But the idea now of this short introduction is more or less rather taking some terminologies, bringing them into context, then have a little bit of view on what is now the relevance for HPC and AI, and how you could use that, right? When you think about you want to adopt the AI framework, now your question would be, what would be building blocks? How would I start? So I give you some examples on that. And of course, I think the way how you can understand transformer models, it's very good to see it's quite different from other, let's say, more conventional computer vision approaches we have today, like convolutional neural networks. So I give you some illustrative examples how they work, just to contrast it better to transformer models, which are then rather going into the idea of sequences of encoder decoder models, where you need to have a lot of, let's say, AI knowledge already, essentially to really follow through. And I mean, basically, many of you know that RNNs have been there. So the idea of working on sequences is definitively not new, although you heard now the breakthroughs, transformer models like BERT, GPT-3, breaking, of course, all sorts of records in machine translation, language models at large. But here the idea is also to think a little bit what was now the difference between these RNNs and LSTMs and GRUs we heard already, and really to make an easier transition then to the transformer models, where I just will show very, very simple basics, and then Christian takes you on the journey of really understanding the cutting edge of these transformer models as an expert. So fasten your seatbelt for a very quick ride through machine learning as such. Basically, when you think about machine learning, you would have always 3 ingredients. You would say there should be some pattern, right? So before you go and do some machine learning, you would think you don't want to learn a random process. There must be something, a pattern, some, something you want to uncover that you want to learn. On the other hand, if you then would have a perfect mathematical formula for this interesting pattern, then you basically don't really need machine learning. You can maybe do surrogate modeling, or you can basically do some other things. Might be interesting, but usually would not necessarily need to go for machine learning. If you have a perfect mathematical formula, you go ahead and implement it. So this would be, of course, also not the best approach, perhaps, especially not in the beginning. Perhaps later you augment it with machine learning approaches. And of course, the key ingredient is data exists. I think that's pretty clear. Machine learning means learning from big data these days. This also brings us to the topic of that these approaches that we have in the project are, of course, shared with many different signal processing communities, data mining, applied statistics communities. So this is something where in the recent years, there has been a term coined where you would say in the middle, there's some overlap where we all call that data science at some respect, maybe fueled a little bit with the advent of really having much more computing available that we maybe had 20 years ago, which really means then for us, high performance computing, something is really of relevance in CoE RAISE, at what can transformer models really nicely leverage by basically digesting the data or the input data all at once, which is a small difference perhaps what we had before in RNNs and LSTMs. And let me come to that later. Also from the idea how you learn from these different models is quite different. I would say you can categorize them roughly in 3 different areas, although of course each of these areas would have also their subsequent specialities. The by far best understood these days is supervised learning. There you would have, let's say, 2 already established classes here as an example, Iris setosa, Iris virginica, 2 flowers. You see the image of a new flower, and then you want to know, is that this or that flower? And from previous records, you have lots of annotated examples, labeled data, as we know, basically, or as we call it, where we basically know what each of the different flower is. And if a new image arrives, we can easily train a system, basically that can then differentiate between this or that flower based on some features. So it's a very trivial example, perhaps, but think about that. Of course, in science and engineering, we have quite more complex problems. You see here on the right-hand side, a remote sensing data set, for instance, with hyperspectral data sets or multispectral data sets reaching into different, spectral channels with, reflections of the Earth's surface. So let's say 200 dimensions of the data, not only a couple of features we have to choose from. And the idea is to then identify from these spectral channels somehow the land cover. So can I do a classification basically by learning from existing land cover, what basically would be new pixels in let's say, other images obtained from satellites. Just one other example where you see the different complexities. Now, transformer models would rather fall into another category. You would say it's rather a little bit going to the unsupervised learning. I think also Christian will explain you a little bit more the representation learning, the idea of learning something from the data, which is not so supervised. So you basically have to learn it yourself, where, there are different models in the past. One was always known as kind of clustering. For instance, you see here, for instance, a brain data set I was working with a long time ago, where basically you have different cortical layers, and by their density, meaning the Euclidean distance between the different, let's say, layers, you see really you could cluster this and then identify different cortical layers. Algorithms like DBScan are basically then in an unsupervised learning fashion, just by having the idea of a Euclidean distance, maybe, understanding their something like the distances and then building up bigger clusters as having a so-called higher level data representation. But we will learn today with transformers, with embedding, with having a much, much higher space in this much more complicated setup by making much more possible, which was basically taught at this time with these kind of clustering algorithms. At the third approach, you would call it a little bit like the semi-supervised way or reinforcement learning, where it's almost like a toddler learning, don't touch this hot cup of tea. It's basically something, okay, no smoke is coming out. So by iteratively doing this, pain and gain, I basically learn, don't touch a hot cup of tea. And, when the smoke is gone, I probably learn, okay, I can touch it again. This goes even to high approaches. We also look a little bit into higher level approaches. We look into CoE RAISE. Here is an example of using reinforcement learning then for network architecture search, where you basically can reuse then these learning models, of course, of creating better neural network architectures to differentiate or to classify images. But this is already a far topic and also a topic for another seminar or training. So let us proceed a little bit just by having an overview of machine learning terminologies and where is now really the computing which is relevant for CoE RAISE really in the system. And this is, of course, a little bit now here in supervised scenario. You would say there's some training examples with their features given a vector X. It has this annotation that makes it supervised with a label. So I always know which pixel I, for instance, here in the remote sensing data set talk about. So is it, let's say, water? Is it trees? Are this basically soybeans? So it can really, from this label, derive a little bit. It's not at all that simple. There are mixed pixels, etc., with different, let's say, flowers on, for example, but at least you have something supervised given. We somehow assume in machine learning that there's a given probability on it. So of course, the training example should be more or less created from the same content or the same probability distribution. When you think about learning from Netflix and examples, and also from Amazon Prime, and like merging all different movies, you would say it's maybe a completely different probability distribution, different features, what these Netflix and also Amazon Prime, basically providers will store in information about you as persons, but also about the movies. So this might be something where, you mix different things. So there we have to be a little bit careful. And in one respect, you would say some point in time, this data was created by some target function, but luckily we don't have to know any of this. Basically, what we rather really need is the training examples, which could be high demands for storage these days. So big data, and I think also Christian will make the point with Earth data science, basically there are data sets which are growing enormously into the petabytes these days. So that's getting more interesting to then digest this data, putting that into machine learning. And then you see here from the hypothesis set, that's something what you will say is a toolbox. The toolbox basically of machine learners, I would say, do I use a neural network? Then I need a learning algorithm, which is for us, for instance, backpropagation then, or you do here, as an example, support vector machines, and you have quadratic programming. So you would say always this hypothesis set goes with some specific learning algorithm, and over some error measure, we basically creating hopefully a model over time with computing to create a final hypothesis, which more or less out of these, with all the different parameters, will approximate this unknown function at some point in time. So learning from this, of course, is now the computational intensive factor. So this learning algorithms really in the fit function can leverage HPC of orders of magnitudes. Once we have a trained system, the benefit is, let's say, more on the throughput level. And one example is what you see here quite nicely. Here you see just modular HPC systems, as I was alluding to in my welcome already, where this is a theme, how we create supercomputers in Europe towards Exascale. And when you have now this learning algorithm, of course, you have a way how to want to deploy this. One idea would be to use extreme scale booster, which uses a high number of GPUs. Oops, sorry, I have some background noise. If you could please mute, that would be nice. Thank you. Then basically here you would maybe take the extreme scale booster, which then has a high number of GPUs, where you would deploy the algorithm. And of course, there's where the RAISE framework comes in with all the different technologies. You have seen PyTorch, you have seen Horowot combined with TensorFlow that needs to be basically ported on this system. And this is, of course, then something where we do lots of studies in RAISE. I just show you here that basically shows a bit the relevance of the DALI data loader when you think you want to compare maybe PyTorch DDP at scale or using Horowot for distributed deep learning training here with lots of GPUs going to 1000 here, where, of course, the idea of HPC is, but you also see it's not at all that easy to just throw that then basically on the supercomputing resources, but rather also think about the drop in efficiency, right? And this is something also what we study, what could be approaches, different learning rates and so forth, which are not now directly relevant. So I skipped that topic. Just that you know why we're doing this is all thinking about HPC. Of course, we don't want to have the laptop anymore, basically with one GPU equipped and then maybe training for 3-4 hours. But as you also will see, perhaps in Christian's talk with the GPT-3, you're not in a couple of hours, a couple of days to train that. So these are really large models which leverage HPC and which takes, otherwise an infinite amount of time when you have just your little laptop workstation. So it's basically not possible even with memory. But anyway, long story short, GPUs help a lot in deep learning today. We will face the heterogeneity of those. The accelerators are not anymore just basically NVIDIA. We have also different AMD Instinct cards and so forth. And of course, quite nicely, you see also here, when you think that quantum annealing can maybe play in the future sort of an accelerator. I wouldn't combine it directly like GPUs, but rather as saying you compute basically your machine learning models, but for some optimization steps, you would basically leverage the quantum computer. As some of you know, the quantum annealer comes back with an answer very quickly, right? There we talk about really seconds, and we're using this then basically back in another module and continue then with the optimization results. So this is one of the facets where we also in RAISE look in, which is, let's say, cutting edge in HPC these days to really combine these different models that we have there. How you use this is quite different. Some people use batch tools, but for our AI community, folks that are actually looking into this, we have now also adopted more and more the Jupyter tool in the HPC system. So that means you can really nicely use Jupyter notebooks, Jupyter labs for sharing also with more different team members. Of course, it's much more easier. It's much more, user-friendly if you want. Also in terms of basically having outputs in visualization or integrating other Python packages, which are quite relevant. We in JSC at the Uli Supercomputing System use the Jupyter system, which is also accessible to our user there, and where we also offer the RAISE framework basically to be used with. So if you have interest, please contact us, and then we can also think of helping you a little bit with computational time. Of course, this is a factor in HPC. I should say the HPC systems are not completely, let's say, directly usable at scale. With 2000 GPUs, you usually have to have some time grant on these machines. However, if you want to collaborate with us in RAISE, I think there are also ways how we can engage users early in the process, how we can help to get these computational grants, and then, of course, also have some benchmarking time and some, let's say, application enabling time, as Praise would call it in the time of Praise. We're now transitioning to Euro HPC, so that means there are lots of new modus operandi, but based on the same success principles we have learned from Praise. So also there, RAISE can help you a lot to get access to these systems. Now, to contrast transformers a little bit to the traditional way how you would maybe do, for instance, image recognition, I have brought you here the MNIST example because it's very easy to understand. There are 10 different characters here that you see. Your digits you want to basically classify. There's a nice data set called MNIST, which has this handwritten digits, and you want to create a machine learning system that basically is recognizing all of this. And of course, I don't give a big tutorial here. You just see a little bit how the training and data set will look like. And I'm sure you find on the web a lot of different tutorials on this particular data set. But the key message is really, we have here something we would say is a kind of 2D input. You see here different gray scales, which then sort of creates the digits. And then you have training and test sets. But you have this label that is important now to notice, because this label will be a little bit different when we talk about transformer models later. This brings us to a supervised fashion here. So we always know a bit basically what these digits are there, and we can learn from that. That makes it a supervised learning scenario. Still, the idea of a training and test set remains also for more elaborate models. And when you do this, you can use nicely Python. I have here an example of using, I think, PyTorch with it, which you can then, of course, on top use with Jupyter notebooks quite nicely. And that can actually do the task and fit a function very nicely with quite some good accuracy to get these labels and correctly classified. So you look at an image, and then basically based on the grayscale, you can recognize this. The idea now of doing this with deep learning is a little bit encapsulated in this particular image, where you would say now you have a so-called convolutional neural network setup, where you learn features in the data. And that brings us a little bit also to the idea later that also Christian will, with representation learning, allude to. This is a little bit different and really looking here by image, right? So image by image would be learned and not the whole data set at once. So image by image, I try to get features out of a 7. And you see that with different filters here, learning really smaller features until you then in the end put that to a softmax here to really get some probability. Is that a 7, an 8, a 9? So the way how that works is essentially really independent from one data item to another. Hence, it's not really a sequence. It is basically the batches that have all the different images. You could also say it as a signal all at once, and you learn and learn. Of course, iterative through all epochs. You learn through different mini batches and so on. But over time, you can also show with a convolutional neural network, you have, of course, very good examples for this particular data set. So it works and is, of course, something where you think is these days more or less cutting edge for computer vision. However, we will see in the second part then with transformer models, there's some role to play in the idea of using this for computer vision as well. They're generative models. I will talk a little bit about just to get you, let's say, grounded on the idea of sequences, because now we were talking about essentially one image at a time. Now what happens with sequences? Of course, also there, machine learning has a long history. Called recurrent neural networks that I will explain a little bit, and then more cutting edge ones, which were driven by deep learning indeed, or are driven by deep learning, called long short-term memory and gated recurrent units. So when you now see the 10,000 feet perspective, really the difference that basically transformers then add to those is the idea of this attention mechanism. We will hear today a lot of it, which is basically derived from the fact that you process all the data at once for sequences. So no, we don't talk anymore basically just of doing, let's say, image by image and having, let's say, just parts of sequences looked at. Here we kind of process and create weight matrices for all the different, let's say, tokens that go into this. It is an elaborate topic, just to think a little bit about now the difference to transformers that we had in the past. And I'm sure many of you have heard these pre-trained examples, which are very popular today on Wikipedia corpora of different sorts of corpora, which is available to the community. GPT-3 is one of them, which we here have in teaching every now and then for the students, but I think we will also come back later. The general principle, however, is that you have, of course, a sequence, and I think this shows it quite nicely, how basically the past was tackling this. So you had basically not anymore a feed-forward neural network in typical artificial neural networks. So here you have to think about a recurrent structure because you want to have the time, so to speak, and this time in terms of sequence reflected. So you would have this unrolling here of this self-connection, so to speak, which gives you then different inputs and outputs in this recurrent neural network models. I give you here a little bit an example of how that looked in when you want to have, let's say, in hello, and then, predict the next character. You would do something like this and look in a H, and you would have learned something which says, and okay, there would be probably an E coming out afterwards. And you have certain probabilities here that says it should be an E or maybe something else. But that's how basically recurrent neural network learned over time, always having, let's say, given in the signal from the last time step, but also, of course, a new signal that's coming in from the sequence. A very simple model, but very old model, and had done the job of some problems in the past. Obviously, in contrast to many of the different sequences we face today, We have much better results with so-called long short-term memories, but you have to pay the price for it, as the figure already suggests. You see here with the different gates of a forget gate, input gate, and so forth, you fuel something we call the long short-term memory, which you see essentially going through all these cells here on the top. I still give the signal from the last time step, so somewhat into the cell of the next time step, and of course a new signal coming from the sequence, but I also maintain something like you would call a reference window or a kind of memory I look at. So this made it very successful because the recurrent neural networks per se, as you see here, don't really have this kind of reference window, or at least the long perspective on this. So RNNs, in contrast to transformer models, is really, let's say, prehistoric, but the approach of RNNs, which is reflected in basically gated recurrent units or LSTMs, as you see here, is of course valid to look basically in the time step. You tackle the sequence at once. What you see a little bit also here, then now contrasting it to transformers, alluding a little bit and coming closer to Christian's talk now, where we have to think about that basically with the recurrent neural networks, you cannot have the whole data set looked at, right? And this is now where the attention is coming to, but it's not that simple as just digesting the whole data and then be happy. Instead, you also tokenize it and give weights to different importance of words or focus on different words, which then brings the attention to attend to certain elements. So how that works is, of course, something which I think Christian will talk a little bit longer about. But here's one key example where you think, depending on the input right now, you would have learned basically relevance to other words, and you call it maybe more generally tokens, which are basically in context. And now that's the important part. While you have everything basically at once in the data learned, you still have the relevance of the context. However, you're not limited in the reference window that we have seen that is too small. So you have a reference window which essentially is in principle infinite, right? And that's, of course, it's basically where the HPC now comes from. It comes into play, basically, not only for training these models in terms of speed, but also the memory availability to have these large models trained at scale plays a big role to enable then, of course, also that you learn these different weight matrices over the whole corpora or the whole input that you basically generate. And by the recursive nature that you have also in the RNNs, this was always a little bit limited of what extent you can use HPC. Here, the transformer models with the encoder-decoder structure have also, let's say, a more easier way of parallelizing that, which brings us also more to a benefit why in CoE RAISE in basically our national competence center that makes sense to use. Right, and basically to just pull that now on the table here, I think we hear a lot from this from Christian. There was one famous paper I want to just highlight here that was a couple of years ago from Google that then basically had the general 10,000 feet perspective of learning representations of the data all at once with this attention mechanism. So you have here, however, several cells which are very special, creating then different weights in this attention mechanism we have here in. Of course, the general operandi of an encoder-decoder, like we had also in the RAISE video about autoencoders, remains the same. So basically, you have an input, then you learn the representation. In the autoencoder space, if you remember a little bit from the video, we had this latent space, which we learned. And here you have basically a continuous representation of the data based on all this, let's say, what we have seen here, the context relevance, so to speak. And then, of course, you're just reusing it in the decoder, right? So basically, you have then this representation learn, and then, of course, you can reuse this to generate. And this is something where this GPT models can be, for instance, used as pre-trained models a lot to really create even novels, if you want, or actually text phrases out of learned text passages, which is one of the famous use cases or basically, demonstrators of these models. And the key is really the attention mechanism. So here, I think I would also more or less refer to Christian and stop here with my teaching slides. That this is, of course, something which is quite nicely in terms of an idea. If you break it down, it falls back to some building blocks which are inserted in this encoder and decoder architecture, where really lots of weights are trained. Also, when you think about the LSTM and all the different gates, this was not at all very simple. So each of the different gates had the different weight matrices that need to be learned. Equally here, you have basically all the different tokens coming in. And then what you sort of create is a query really with a set of key value pairs, where you then also have to basically learn over time then these different, let's say, weights that you assign to these different, let's say, more or less in sort of lookup table, right? If you want to see it on 10,000 feet perspective, in order to see the relevance now of the word in context that is a bit expressed with this interesting arrows that you see here. And then you can do this not only, let's say, in one scale, you can train, of course, like we have seen in the convolution approach, perhaps a little bit the analogy, you can train different on them, a bit multidimensional, which is suggested here a little bit. But I think in light of the time and having Christian here on board, I stop here. And of course, refer to questions later. I think some of your questions are probably also clarified by Christian. Just some thanks to my research group, which give me some of the results that you have seen here. So now the time is for Christian to share your slides. And I would just say, go ahead.
All right. You hear the slide? You see the slides? You hear me?
Yes, I hear you, and the slides are seen. Perfect. Thank you.
Okay. Then first of all, thanks for the invitation to speak here. And yeah, just to say, if there are any questions, you are also welcome to just ask them during the talk. Despite it being somewhat meant for the YouTube audience, I think maybe there are points that are then of interest and relevance for other people. And so please just unmute yourself or raise your hand if you want to ask a question. Yeah, I also want to build a little bit of a bridge in the talk to essentially more of a classical high performance computing and computational science and engineering domain. So I will explain the transformer essentially not from a machine learning perspective, but a little bit from this perspective. And I hope this makes the whole subject a little bit more accessible. Last week, a fairly senior person told me that this would take away all the magic of a transformer. And maybe that's true, but I'm a scientist. And I think the job of a scientist is to take the magic away and to make it explainable, understandable. Just very briefly, my background, I did my PhD on simulations in computer graphics. I did afterwards a lot of classical simulation and modeling, light, fluids, adaptive schemes, including energy and momentum preserving Lie group integrators. And I'm also part at the moment of a DFG-funded large collaborative project called BioCreation, which is about large-scale simulation of reacting gaseous flows and granular assemblies. So there are some connections, I think, to the problems that are actually investigated in RAISE. And the whole point here is I do essentially come from a more classical scientific computing, high performance computing background, not really high performance, but really scientific computing background. So I don't think machine learning in general and transformers in particular are a panacea that will solve all of our problems. I think it's a very useful and effective tool for certain problems. And I think in particular it's complementary to maybe our existing tools, but I still think you have to select based on your problem. You do cover and raise a fairly large set of problems, so I don't have an answer for all of you. And my talk certainly won't do it. Maybe we can talk a little bit about in the questions and answers, or just get in touch via email if you want to discuss any further. But I think there's a little bit, I try to give a little bit of a general perspective on what is the idea of transformers and representation learning. These are not, they are correlated, but not causally connected. We will talk about this. I will also use, as Morris already said, weather and climate as the running example throughout the talk. That's the problem I'm working on. That's where I use transformers for. I will try to always pull back a little bit from a specific example, but for a moment, I think in general, we have to learn from specific examples and see what works and what doesn't work. We are not at the point to build big grand theories yet, so we have to start with specific examples. With this, let's start a little bit with a motivation, weather and climate, and why machine learning makes sense there. So that's essentially a plot of a relevant scales in meters on the x-axis, on the space dimension, and in time on the y-axis. And what you have essentially in weather and climate is that you cover about 10 orders of magnitude in space and time. So these are the relevant scales you essentially have to simulate if you really want to do weather and climate simulations. And even if you take an exascale computer and what comes after the exascale and what comes after and after the exascales, you won't be able to simulate this with classical approaches. One reason is, yeah, there's just not enough compute, even if you go 2 generations past an exascale computer. The other reason is we do not actually have physical models at small scales. And even if you have physical models, for example, for cloud formation, the physical models are really for, you have a very small dust particle and the cloud forms out of this dust particle. If you take a simulation where you also have to simulate waves that are on the order of tens of thousands of kilometers, which just won't fly in any way. So, and there are many phenomena, for example, for the interaction with the biosphere, where we do not actually have any equations. In principle, you could sit down and try to come up with equations, but there are just many of these phenomena where we have no understanding of the physical laws. However, what we do have in the earth sciences for these cases, we have a lot of large amounts of observational data. So these are here just to give you a sense of the scale. So ERA 5, this is essentially a collection. It's called a reanalysis. This is a collection of, you take all of historical weather measurements, you interpolate them and put them into a coherent data set. So if the latest generation of this are around 6 petabyte, then you have here the CMIP6. These are essentially the large scale simulation that I run for the IPCC climate report for the UN. So there's an order 100 petabyte, give it and take it, maybe 200. Nobody knows, I think, exactly. And you also have more direct observational tools. So these METOP satellites, this is the next, I think they start in 2023 or 2024. This is the next generation of the ESA satellites. So we just generate of raw observational data, essentially multiple terabytes per day. So if you would take all different satellites then together, you can easily estimate just on a daily basis, you will have 50 to 100 terabytes of data that is coming in. And there you have a similar for the ocean, also like these large data sets on the order of petabytes. And this is growing very fast. And what makes this really interesting from my point of view, that this is observational data. So this exactly covers some of the aspects for which we do not actually have analytic models. So this is why I do think weather and climate is actually one of the cases where machine learning makes a lot of sense, because we have these large amounts of data and it is actually somewhat complementary to where we do have good analytic models. On the large scales, we know Navier-Stokes holds a very good approximation, and there's little doubt that we can build efficient standard classical numerical solvers for the large scales. But for the small scale phenomena, we just don't have models, but we do have high resolution observational data. How to use this data for machine learning, however, is an issue. Because Morris just explained it, the standard methodology is right, we have supervised training, but essentially all of this data is unlabeled. And there's no way you could possibly label it, right? Like for image classification, you can take Mechanical Turk and put out enough money, and then you can essentially label even 100 million images. But there's no way there are like 1,000, 2,000, 5,000 people who could potentially possibly label this data to say that this is a storm of category 3 and this is this kind of special phenomena. It just wouldn't work on a petabyte scale. Right? Another issue with this data is that you do actually need supercomputing infrastructure to store it, to handle it. And this is it's a big issue, especially for universities like me, university labs. It's you cannot download it, you cannot process it. The big industry labs also, right? We do have huge compute infrastructure, but it's also limited to, Google, Facebook, Amazon, you can count it on one hand. What are the big labs that can still afford to actually deal with these amounts of data? We don't deal with weather and climate, not yet. We are really all moving into this space, interestingly, but it is essentially the same scale. So 1 to 10 petabyte, that's roughly the scale of data the large models are trained on today. So, and the big industry labs do have the compute infrastructure to do it, but only they. Right, and another question that is more relevant than in the context of this project, how do we actually ensure that our learned models are physically consistent and physically reliable? So, to make this a little bit more concrete, right, one very important application is hurricane tracking, very classical. You want to know when the hurricane hits the land, where it hits, at which strength it hits. We do have classical models for this, but people are also working on machine learning models for this. if you actually look at what training data is available for this, these are essentially all known historical hurricanes. It's 6.5 megabytes. So, right, so like you have these 6 petabytes in reanalysis, refractory analysis, and then to actually label data to solve your specific problem, you have 6 megabytes. So that's, you can take an old floppy disk out and you can just send it over. So, and this is one of the big challenges, right? Like we face in a lot of science and engineering applications. We often have, you have maybe a lot of data. It's also not true for all applications, but often we do have a lot of data just because the latest generation of observational tools, we just have super high bandwidths. So it's in high energy physics, so it's in astronomy. But you also can look at, for example, in engineering, like methods like particle image velocimetry. You also can generate terabytes of data if you have one experiment and do many runs. So the question then is, how can we actually use these large amounts of unlabeled data that we have to solve our tasks and problems where we really in kind of some sense need labeled data to train on? So, and this is essentially where we get to the first part, self-supervised representation learning. And and what is the idea of this? And so self-supervised representation learning is a very classical subject in machine learning. Maybe that's to begin with. So the second quote, so these are both quotes by the demigods of deep learning who won a Turing Award, so the Nobel Prize in computer science for their work on deep neural networks. So the second one is by Yann LeCun, self-supervised learning, the dark matter of intelligence, and it's just from this year, I think. So that's, as you know, the dark matter makes up 80% of the universe. We just don't see it and typically only see indirectly the effect. But in the big machine learning labs, it's just self-supervised learning is a very big topic, which just hasn't caught on that much in science and engineering. The first quote is by Yoshua Bengio, but this is a bit older. And he says that human developed representations and abstractions to enable problem solving and reasoning, and our computers should do the same. So, and here's this representations, that's the key part. So what is a representation? On the left, we have a neural network. It can be any neural network, it doesn't matter. It looks like an MLP, it can be a transformer, it can be whatever. It doesn't matter too much. It's just, you have some kind of layer structure, and what it does, you take an input, you take its input and vector on Rn, that's essentially what almost all neural networks kind of agree on, and you map it to a vector on Rm, and you iterate this process for all the different layers, or blocks, or however you would like to call it. So what you just, by construction, end up with, at every layer, you essentially have always a vector in Rm. It's a mapping from a vector to a vector, so you always end up with this vector in Rm, and you have this at every layer. And the idea of representation learning is now to essentially take this vector you end up with, this embedding into a vector space as the central objective of a learning. So here we have this vector in Rm that you put in some vector in Rm. This might be an image, this might be some piece of text, this might be a fluid simulation, this might be some detector events in a particle accelerator. And you take this data set and you map it to a vector in Rm. M might be very large, depending on what you do. And this is essentially what you care about in representation learning. This embedding of a vector, and the central part is here that this is task independent. So you want to train a network that, for example, is specific to natural language processing, but that you can use for a chatbot and for machine translation, or in computer vision, a network that can do image segmentation and character recognition, or maybe in fluid flow that allows you to do forecasting, but also to segment relevant features in the flow and so on. So that's the first part of representation learning. So the point is no longer to solve a specific problem at the beginning, but to have a network that essentially understands domain knowledge. That sounds maybe a little bit ambitious, but there are really examples that now demonstrate that this is doable. Like these GPT-3 models are a very good examples. Yeah. The big industry lab, really, we have one language model. It's just one huge language model that it's trained on for months on thousands of GPUs. And all it does, essentially, it understands the intrinsic structure, the grammar, and of human languages. Typically, we're trained on many different languages simultaneously, and this improves performance. Why? Well, because the networks learn the intrinsic structure of languages, the concepts that are behind the words, and that are essentially important, for example, if you do translation. Good, so that's the first part, representation learning. We try to just transform our data into some feature space, into some vector space, where it's in some sense encoded more efficiently. PCA, Caron-Löwe transform, proper orthogonal decomposition is in some sense a simple form of representation learning. That's a classical example, and it's used already that there are so many names for the same thing, shows you that it's useful. And yeah, that's in some sense the simplest form of representation learning, in my opinion. You don't learn, you have a fixed algorithm that just gives you the answer. And now when you turn it around, you say, well, how can we generalize PCA to a setting where we have billions of parameters that we optimize in a nonlinear fashion using huge amounts of data? Right, so here's an example of a representation the network learns. This is just an old paper from a convolutional neural network. And you see that in the network, you actually see recognizable features. So, and that is essentially the representations the network uses internally to solve problems, and that is also useful to solve different problems. Okay, so that's the first part, representation learning. And the second part is self-supervised training. These parts are not strictly coupled. They are typically used together. There are also counterexamples. You can do self-supervised you can do representation learning with labeled data sets, like Google Brain, for example, does this on vision. Most people think the better way to do representation learning is to do self-supervised training. And self-supervised training is essentially, you do training without labels. And that's the idea. And this is why it scales to very large data sets, because you don't need labels. You can just essentially, you just have a data set, you do training on it. So the crux is, it sounds a little bit nonsensical. You always have to have a loss function that measures how good your network is. And the idea is essentially to generate labels from the training data itself. And let's look at some classical examples for this. So this is sometimes called a pretext task, or these are the classical examples for how this works, how to generate labels, or how the learning objective, maybe more precisely. And one simple example is you do in-painting. So you have an image, you start essentially with a full image, you just crop out a region, and then you tell the network, predict me what I just deleted. And simply because you have a full image and you just cut it out, you clearly have the network, you can use the full image just in the loss computation. And a lot of self-supervised pretext training tasks are some variation of this idea. This idea transformed to a different domain, to a different setting, but you somehow have a data set, you delete some parts, and the network is trained on essentially filling in the missing information. So you can do the same thing on color channels. So you have a color image, you delete the color information, and then you have the image essentially recolor the image. It's again the same idea. It's just essentially instead of cropping out a region in space, you essentially take the channels in the image and do this masking, how it's often called. And the third example that took essentially this idea to natural language processing is called the BERT masked language model. And this is one example that is one of the key papers in the literature for this large-scale self-supervised training. And this is really, we get to the transformer later. So this was one of the first papers that really demonstrated that these transformers work very well. You can scale it to billions of parameters and huge amounts of petabytes of training data. And how does it work? Well, you have as input essentially a sentence, you delete a word, that's the analog of cropping out a region in an image, and then you have a network essentially predict the deleted word. So that's the idea. It's again very similar, just an adaptation of this cropping. And you do this for 2 sentences actually. And then you have, on the one hand, the network essentially has to somehow learn how to predict this missing word correctly. And there are really 2 parts for it. There's a semantic part, what word belongs there semantically, and what work, and how the word, what's the grammatical structure that should really fit in there. And so that's very simple, but a surprisingly powerful task for training a neural network, because yeah, it has to learn a lot of structure. And to encourage the network to learn some more global structure, not just local sentence structure, we also included a next sentence prediction task here. So you have the 2 sentences here, and the network is always asked to give a binary answer if these 2 sentences that are fed to the network do actually belong next to each other in a longer text. So is there some semantic correlation connection between the sentences in the network? And the interesting thing is that, so we trained this model essentially without a specific purpose, or just fill in the deleted word. You could say that's a meaningful task. Maybe you have a scanned book and you have to, some words didn't get scanned properly. So there is an application for it, but the purpose of this training wasn't really to have a network built on this. What we wanted to do is we wanted to have this big network. And then we, once we did the big training, we wanted to adapt it with much cheaper. We had two ways to, in a much cheaper way, to specific applications. This adaptation is typically done in two different ways. One is you just take your big pre-trained model and you do some fine-tuning on label data. For example, you could do fine-tuning for translation, and you would take then bilingual text and essentially fine-tune your model specifically for this. Or the alternative is essentially take your big network, just freeze it as it is, and you would append another network at the end. It's called a tail network for a specific application. And what we showed is that essentially this idea, do pre-training on for just task-specific, task-independent, but domain-specific, and then fine-tuning for specific applications. This essentially gives you better performance than just taking a neural network and training it only for a specific task. So why is this? Why can this be more powerful? The idea why it's more powerful is because you can, the domain-specific training on the self-supervised task essentially allows you to train on much more data, and through this essentially, then you essentially have a network that is in general more powerful, and then you can exploit with smaller amounts of labeled data in a more effective way by fine-tuning it to specific applications. So that's in principle the idea. There are even some examples that show that even if you fix the data set size, essentially by removing the labels and having a very smart self-supervised training protocol for representation learning, you can actually even improve performance on the same data set size. So the data is the principal means typically that helps in representation learning. It's not strictly necessary. So representation learning is really how can we get the network to learn the internal structure of the data rather than getting too specific on an application. And then you fine tune it or you use a tail network to solve specific tasks. Like this is what is essentially listed here. The important point is really the last column where you see the BERT large, that's a large, I think it's already over 1 billion parameter network model, achieves essentially best performance, better than humans, better than specific models in the literature. And the way to achieve this is really through this representation learning. Good. So this is essentially self-supervised representation learning. There are many different ways for the loss function and how to realize this in specific ways. Contrastive loss function is a very popular subject these days for self-supervised learning, where you essentially always try to, you have next to your input, you have one dissimilar, one similar example, and you push and pull. It's the idea of contrastive loss function. Dino is a very interesting work that adapts student-teacher learning to self-supervised training. And as I said, there are many extensions of this BERT-style completion tasks, for example, also to computer vision and to many other domains. And yeah, this graph here is now the translation. What does this have really to do with transformers? And that's the connection here. So this is essentially how the accuracy on standard computer vision tasks scales with the data set size. So on the x-axis, we have the size of the data set, on the y-axis, the accuracy. And blue is essentially a G, with G here, that's a giant neural network. The H here, the green line, is a huge neural network. So we really pushed network size. I think the giant must be around 100 billion parameter network. And what you see is essentially, if you increase the training size enough and the network size enough, you can really get better performance. So there's a whole subject that is called scaling laws in machine learning, and this has been demonstrated in the same way for natural language processing. It has been demonstrated for computer vision. And there's a strong belief that this is a general observation. If you essentially scale data size and network parameters in the same, in a proportional way, and if you are able to scale your training data, then you can get extremely good. You can just always increase your performance to a very long way. A lot of people argue the network architecture at some point, if you're north of 100 billion parameter, doesn't maybe matter too much any longer. But what matters evidently is you need a network that you can train efficiently in a parallel fashion on a high performance computer. Right, so this blue dot here, this took about 4 months on 3,000 to 4,000 GPUs. So, which essentially is outside of what you can get in a publicly accessible computer. So the JSC, the Jülich booster, right, it has 3,500 GPUs, but you will never get 4 months for yourself on this machine. Right, and I don't know, maybe BNL or so in the US would have a machine that could do it, but because you would never get just this amount of compute on this machine, it's essentially undoable for academic lab at the moment to train these models, and that's actually a big issue, right? So like with a little bit, the industry labs get to a point where academia can no longer reproduce the results. So that's somewhat a orthogonal issue.
Not talking about the energy crisis we have, if it's really useful to burn all the cycles so long. But yeah, it's a interesting point indeed.
Yeah. I mean, the argument is right. Yes, it's super expensive to train them, and Google calls these foundational models, but you have to do this training once, right? Like, so Google does this probably every 3 to 4 years, training a new large language model. So in some sense, you could argue it's actually more energy efficient because you amortize these huge training costs over when a lot of applications. And the fine tuning of the tail networks are much, much cheaper. So that's one of the arguments why Google does it, right? And for them, for big companies, we do have to pay for the energy, even if we build their compute centers in Iceland and Greenland and so on. So I've never done the calculations if it's more energy efficient, but I would assume because you reuse the big network over a lot of applications, you have at least the potential to be more energy efficient.
That's an interesting perspective indeed. I mean, on top of it, if you share the models, right, then with the community, this pre-trained models is another way of saying that helps.
Right. And for example, Google, we literally have one big language model that we specialize to chat, right, which actually speaks, I think, 30 languages or 40, I don't know at the moment. You specialize to all kinds of chatbots, to the translation, to the autocompletion, to Gmail autocompletion, all these things, right? It's just one model that is essentially in the background. So, yeah. So, and there are different ways. So there's a comment that also inference is much more expensive. It's true, but once you have a big model, there's like model distillation on student-teacher training to actually get much smaller models that have comparable performance. Unfortunately, at the moment, the only way to get there is you need first the big model, and then you can distill it to smaller models. So, I mean, this is a little bit, we wanted to prove it. It's a research that comes out of Google Brain. We did a lot of this large-scale vision transformer work, and we just tried to prove that it's true. But yeah, it's used in production in Google. And for example, the BERT paper that I showed before, this was, it took Google 1 year until it actually made it to end users. So we adopted it very quickly internally because it was so much better than what was there before. Good. With this, we can get to transformers. So, and transformers are today the standard architecture in natural language processing and pretty much also in computer vision. And if you know a little bit about the machine learning literature, then you know that this is 85% of all the applications that are studied in machine learning fall into these two big categories. So it's somewhat fair to say that this is now the standard architecture in machine learning, which a lot of people find very nice because there's again one standard architecture. You no longer have a separation between LSTMs and GRUs for natural language processing and CNNs and similar architectures for computer vision. There's one unified architecture that essentially covers all domains, and they can learn, for example, by the things that have been discovered in natural language processing for computer vision tasks. And the original reason, Moritz already showed the attention is all you need paper. Original motivation was just it's computationally more efficient. So we wanted to do large scale training in the Vaswani et al. Paper, and the whole paper is essentially about this argument. I think the architecture is very interesting for a lot of different reasons as well, through self-intention and other reasons. But the original motivation was really to have an architecture that trains about, that's the slide here, it's about a factor 4 more efficient than, for example, standard convolutional neural network. Once you go essentially to a regime where you are on the order of 1 billion parameters. So it achieves better performance and it's more efficient to train. So that's the argument, if you typically have enough data. So that's essentially, and here you this is TPU core days. So there's a lot of compute that went in these models, but yeah, it's a factor of 4 that does make a huge difference in the end. Good. So with the transformers, now I want to a little bit explain how do we work with transformers. And this is essentially what we saw before, right? So what, in some sense, every neural network does, it essentially transforms your input vector into some vector in an embedding space. And this is true if you do representation learning or not. Representation learning essentially turns the picture around and really cares about this embedding into a vector space at the final layer typically, but perhaps also at the intermediate layer. And well, since we are in a vector space, what you can do, and that's really back to scientific computing and all these things, right? You can compute the dot product. And the dot product, evidently, what does it measure? Well, it's the angle between these vectors, or the correlation, if you want. So you can put many different words on it. I think everyone in the audience knows how a dot product works, and that it computes some angle correlation between the vectors. And that's essentially the idea of a transformer. To use that in the feature space, we can compute dot products. And this is what is called attention in the transformer. So to make this actually useful and work, we now actually do need multiple vectors in our feature spaces. So that's the first step, and I will explain it for natural language processing because I think it's very intuitive, but I will briefly mention how it works for computer vision as well, and then also for a flow problem. So, right, so we have here actually a sentence. We split up the sentence into different words, and we call these words now tokens. And now we feed essentially all these words in parallel through a neural network. So instead of essentially taking this as one big chunk and feeding it through a network, we now think of the different words as different inputs to the same neural network, and we just feed it in parallel. So what we get is in each feature space now we get multiple vectors, because we get, for example, one vector for sun and one for shining. And if it's a good feature space, you would actually assume sun and shining should be somewhat close by in the feature space. And now we can compute the dot product between these different inputs. And this is essentially the key idea from a scientific computing point of view of a transformer. And this is called self-attention, because you attend between different inputs, between different parts of the input, essentially. So, and a transformer essentially now feeds this into an architecture. So we start with the different MLPs. What the MLPs do, they map between the different feature spaces, right? With each layer here, you have essentially a different feature space. And this mapping between the feature spaces, this is what an MLP is. So that's a standard, that's a standard dense, plain, simple as you can get neural network. Densely connected. You just have essentially a matrix or multiple matrices and multiple nonlinearities. So what is, it's called a multi-layer perceptron. And that's what MLP stands for. And that's the classical textbook example on neural networks. That's what you use to map between the different feature spaces. And in each feature space, we compute the self-attention. And that's essentially what a transformer is. You iterate this process for the different feature spaces that you essentially already looked here, right? So now you have the MLPs that map to the different feature space, and in each feature space, you now compute this dot product self-attention. So that's on a high level what a transformer is. And somehow I think that's from a scientific computing point of view, that's not so strange. We know there are maps between spaces. There are also nonlinear maps, so we are not so familiar with in scientific computing. We try to always reduce it to a linear map. And then we compute dot products between vectors. Good. Let's look a little bit at the details of how this works. So we have our input tokens that were the different words in the natural language example, and we compute the self-attention, which really means we essentially compute the dot product here between the different tokens. I just keep the picture in mind. I think it makes it much easier. And what we typically do, let's fix the token ti. That's where we fix the word sun in our example, and we compute the dot product to all the other words in the sentence. Right? So this gives us some set of vectors, some set of angle coefficients. Like we would assume maybe shining has a smaller angle to sun than, for example, some neutral word like the article. And once you have these dot products here, right, you essentially do, that's a basis reconstruction. That's, for me, it's like That's standard linear algebra. You essentially compute, you fix some input vector, you project it onto your basis vectors Tj, and then you reconstruct with Tj. So that's the idea, right? So you measure the correlation, you project the vectors, and then wherever the angle is large, you essentially reconstruct with the same token. So to make it a little bit more interesting, and this gives you some updated token that then is fed to the next layer. That's the principal idea. So everything here would have in principle a layer as index. I left it off, just we will get a few more indices soon. So but that's the principal idea. So we fix a token like the sun word, and we project all the other words onto sun, and then we take these weights and reconstruct with different tokens. So there's one, to make it interesting, a little bit more powerful, you have here a nonlinearity. That's a sigma here, and that's an soft arcmax. So it's nonlinear. It's not an arcmax, it's a standard soft arcmax, but it's a good approximation to an arcmax. So there is some interpretability and some intuition of what it does, right? Like you would assume a word with itself has the smallest angle, so this is always fed in, and all the other words that are close by, like sun and shining, will also get a large weight here, and so will feed into this updated token. So what it does is some kind of clustering algorithm in the high-dimensional feature space. It's the intuition, at least, behind it. Good. So that's essentially the principal idea of how correlate. So you use the self-attention, that's really this part here. And to get something, an update in the neural network, you do use the weights and the self-attention to update your tokens. That's how it works. And you go through this, you always update your tokens with this formula, you map to a new feature space, you again implement this formula, you go to a new feature space, and that's what is called a transformer. Good. There are some technical details that make this concept a little bit more powerful, and the most important ones is that there are different heads, called self-attention heads. And what's the idea of these self-attention heads? We have now here this feature space at the different layers in our network, and we essentially specialize it. So from each feature space at each level, we split it up into multiple feature spaces. So this is done with a simple matrix, so with just a linear transformation. And it just essentially allows the network to specialize to certain aspects of the data in each layer. So this, you could potentially argue that if you don't use the heads, just make your network much deeper. This would perhaps be a different choice. The standard choice people make is you have not too deep network, but you use many different heads in each layer. That's to essentially have different features. We will see very soon an example of what this means and how it looks like. Has a nice interpretation. And this is implemented, as I said, so from here, from a feature space, you get through the MLP that maps you here. You have a matrix or different matrices that map you to with different heads. So the H here, that's an index that runs over the number of heads. And then you have here, that's called query. This means this token here. K, this means this token here, and V, this means this token here. So that's a historical artifact from natural language processing that's called query, keys, and values. That's how a dictionary works. You look into the dictionary with a query, and you get back essentially a value. It's a little bit of a technicality, I think. But yeah, you essentially use different projection matrices into the heads for this token, for this part, and for this part. So that's all it means. Why is this meaningful? It's again somewhat an architectural choice, and people have tried to use just one matrix. One can argue a little bit about it. There's nothing set in stone. What does it do? So we have now here, we project the different tokens onto the heads. That's when our tokens have heads, right? And all it means is that we have vectors in the smaller spaces here. And you can actually rewrite it if you just take essentially our dot product formula here. And yeah, now you rewrite it with this W matrices. That's how it looks like. The dot product is just the transpose of a vector, transposed with the other vector. Now we have our matrices in the center. And what it is really, so here you have one big matrix. So this is essentially a learnable inner product. So you kind of, for each head, you learn one specific inner product that is adapted to a specific feature of your data. So nobody enforces so far that this matrix is symmetric and positive definite, which would be required strictly to have an inner product. Nonetheless, there are many generalizations of inner products in the math literature where it's no longer symmetric and no longer positive semi-definite and so on. So that's just to give you a little bit of intuition of, right? So like the dot product is essentially the diagonal inner product. And with these head matrices we introduce here, we have a non-diagonal inner product that gives us much more power to measure different aspects in our data. So good. So that's our learnable inner product. And that's what we do with the dot product, and it's just called the attention. It's called strictly self-attention, and there are different attention mechanisms in the literature as well. Like the dot product attention is by far the most common one. And so I would say we start with a simple and the vanilla architecture that has proven to be very powerful in the HR model. Good. Any questions at this point? So, right, key parts. You feed multiple inputs to the network, or you split up your input into multiple small parts. You compute the correlation between the different parts in different feature spaces using the dot product. So standard from a scientific computing point of view. And then you always map to a different feature space. That's a big idea of transformers. Yeah.
Maybe a small question for that, where I'm thinking, you know, when you have now language in a way is nice corpora, but also language can be sometimes written by stupid people, perhaps, that write the grammar a bit wrongly. The same way I think about, you know, when we had now remote sensing, we have pixel-wise classification, and there's, let's say, a class called soybean, but there's also a class called soybean and water, or there's a class, you know, mixed pixels. What I'm getting to is, do you have some experience how noise is dealt with? Because, you know, when basically noise in the sense of wrong grammar, mixed pixels, you can have this in all different fields, right? That the input data is rubbish in, so to speak, sometimes, and that makes usually rubbish out, as we know from AI. How sensitive are these models, and how you would have you there some experiences on that?
Yeah, the point is these models essentially, one thing, you train on huge amounts of data, right? Like if all your data is essentially contains grammar errors, the model will learn incorrect grammar, right? So like that's a true, if you have essentially, if you take Wikipedia and standard block entries and so on, the model will essentially learn good grammar, but it will also know that there are people who speak incorrect grammar. The important thing to understand about these models, and I will maybe get to this a little bit later, right? We really learn a statistical representation, right? Like if you do a natural language processing, if you do, for example, translation, that's the simplest example, right? You cannot just take a word and then there's this translation to this word, right? This is the rule-based methods people try to do, which never worked. The key point is that you have to keep an internal probabilistic representation. And that's how the network also deals with essentially these noisy data with inputs that are, you just essentially have an internal representation that has a higher variance. And people have looked at this to a certain extent. You can really see this in the network, that the network is unsure. But yeah, that's a principal way for a network to essentially deal. If it has an input that is just inconsistent in itself, for example, it doesn't make sense, it will just have a very noisy or very probabilistic representation where, for example, if you have it trained for if you fine-tune it for classification, it will give you an answer where it's fairly uniform above the different answers. But in principle, the idea is large amounts of data should be able to compensate for this as well. So that's also one of the points of representation learning.
Right. The follow-on question would be then, is this not something you would basically see in the heads? You say there's some stupidly learned feature space in the heads from this noise, which is not probabilistic, you know, or statistical often enough. That's too simple to think, perhaps.
How to specifically diagnose it in the heads, I don't know from the top of my head. I would assume essentially you get fairly uniform attention weights. That's probably one of the things. I think we anyway get to this, like we can just quickly pass forward.
Just go ahead. I think it's not a problem. So let's go ahead.
We get to this point in a minute again. So that's essentially the transformer architecture, maybe more from a standard scientific computing point of view. That's just because everyone still copy paste the picture from the original paper. That's how the original Vaswani paper drew it. You have your inputs, that's your stream of tokens, the different words in a sentence, different patches in an image. There's an input embedding. Typically, this can be just a matrix that somehow maps your inputs, for example, 16 by 16 pixels into a 512 dimensional vector. In natural language processing, you have specific encodings that maps each word to some vector in the feature space already. Different answers where it can be a very important part, but in the simplest case, it's just a matrix. When there is a positional encoding, what does this mean? Well, in the transformer, essentially, you have just vectors in the vector space, so there's no order. If you think your input should have an order, like the different words in the sentence, you have to somehow encode it. It's a specific subject where good answers for this in the literature. That's why I won't talk about it too much. But if your input sequence has an order, you have to tell the network about it. So because the different vectors you get in your feature spaces, they are just, it's a bag or it's a set of vectors. And then you have essentially this multi-head attention. That's what we just talked about, right? Where you take your big feature space and you split it up into smaller feature spaces with these W matrices. You compute with the scalar product, the attention, you reconstruct, and you get the output tokens. And here, so you have always a normalization that is also there, and it's a residual connection, makes training typically better in any case. And then you have this MLP, or called a feed-forward neural network, that's a different word, and it's also a residual connection, they are norm. That's the two, essentially, I didn't have these two blocks here in my bigger, higher level diagram. They are clearly important, it won't work otherwise, but it's less, I first wanted to focus on the conceptual aspects, maybe let's put it this way, right? And Morris already mentioned this, so what we looked at so far, that's really the encoder part of a full transformer. So you have typically, that's the part we looked at, and that's called the encoder. It takes essentially the words and encodes it into feature space. And that's what you would do, what you use in representation learning. So if you do representation learning, you just typically have this part. That's also why I started it. But that's an important point, and that's what is often forgotten, is that the transformer is actually, it's a generative model. So that's the decoder part that here you would think of it, take English words as input, and it spits out German words through a translation. And how it's coupled is through a really you exchange here, essentially the tokens are mapped from the input from the encoder network to the decoder network. And then here you have essentially a feedback loop where you always predict the next word, and then you feed in the next word, that's what we see here, back to input. Since I'm not sure I will get to this, I do think just this model here is extremely natural for all the simulation stuff, because what you do, you predict a time step called a word in natural language processing, you feed it into the input, and you do a next prediction. So this here is really a network that is essentially made for simulations for time stepping schemes. So nobody has done it. But I think another reason why I think a transformer is actually a very useful model, right? Yeah, so that's essentially the part that replaces an LSTM and a GRU in the transformer. It's this decoder part here, but yeah, it's ultimately much more general and much more flexible. And I think it's also much more simpler, in my opinion, than an LSTM. Whenever I look at the diagram, it seems to describe an LSTM, I get confused, I have to admit, I think. Yeah, so for me, this idea of computing dot products, I've done this for 20 years without neural networks, so I know what's happening there. Good, so this is the full transformer. Again, I won't really talk about the decoder. Architecturally, it's exactly the same as the encoder part. So you have the self-attention, you have a feed forward, and you iterate this block. So it's structurally, it's nothing similar. It's just that you couple essentially here between the parts. And you would essentially train this part on English and this part on German, and conceptually, that's how to think about it. Good. Let's return a little bit to the bird, because I wanted to show a little bit how do these correlations, right? We compute the dot products. You would expect that exactly that. Close by words have higher, should be smaller angles, or no, the angles should be smaller, or the cosine should be larger. And that's from the original Vaswani paper here. We looked at this example. We took a very complicated language, complicated sentence. The law will never be perfect, but its application should be just. This is what we are missing, in my opinion. So that's the sentence we looked at. We essentially fed these tokens into the neural network, and then we compute the dot products, and then we plot the dot products. And that's that's literally the dot products, what you get out. And what you see here is that, so you have a small angle, a large dot product between, for example, the law will never be perfect. And from a linguistic perspective, this makes a lot of sense, right? So what you see here essentially, like, these are low-level grammatical features. The law, it's the noun with its article, will never be perfect or will never be, right? That's a verb construction, and so on. So the network essentially, like, the feature spaces the network learns, in our words, are actually semantically meaningful, and they are human interpretable. And that's one of the points that is also often made about transformers. It's a model that allows for natural interpretability, introspection. You can actually look at what the network does, and surprisingly often it does something we humans also find useful. So, right, so like, maybe this again takes away the magic of neural networks, but I find it reassuring that the network actually does something I can understand. Right, so this is really like what we plot here is the cosine of this angle. And now you can look at actually different heads, right? We said we take our feature space and split it up into smaller feature spaces. And if you look at the different heads, you see that this is one head where you get these low-level grammatical features, right? And it's the second head here. What you see here, essentially the big sentence, the law will never be perfect, but its application should be just. Here, this head actually splits up this big sentence into smaller sub-sentences. The same way as a human, if you read this long, complicated sentence, right, we would essentially parse its sub-sentence by sub-sentence and subsequently then try to make sense what the author actually tried to say with this whole big construction. So that's one of the things I also find, especially from a scientific perspective, interesting. But it's also, I think, from an engineering perspective, it gives us some confidence that the network might do something useful and reliable. Just if you look, for example, at these are called attention maps, right? So it's just with dot product in the feature spaces. Good. One interesting aspect to mention, so the language and natural language processing with transformer came out in 2017, and it was essentially within a year, it was a model everyone was working with. And then it took about 4 years to adopt the transformer to computer vision. So, and what was the issue there? Well, the issue was actually, if you take an image, how do we define a token now for a natural image? And people have tried various different things. The most common choice was actually to use a pixel as a token. But this has essentially two big issues, using just a single pixel. The first issue is, right, we compute these dot products between vectors. A single pixel has very little internal structure. It's essentially, in the best case, it's a three-dimensional vector. So just these dot products essentially never worked very well because there was just not enough structure in a single pixel. This was the first issue. The second issue was you get an awful lot of tokens, and that's essentially a big problem with transformers. It scales quadratically, the computational complexity scales quadratically in the number of tokens, right? You compute a dot product between each other vector. And if you try to do this in a nonlinear optimization, that's problematic. So there's a limit to the number of tokens you can efficiently deal with. And so these are the two reasons why a vision transformer or transformers didn't work out of a box in computer vision. The key insight was when that's a paper by Google Research, a token is, or a word is 16 by 16 pixels. It's, from my point of view, that's fairly natural, but yeah, it took people 4 years to figure this out. But what is a token? An image should be a small image patch. It should be big enough that essentially it has internal structure, the dot product makes sense, and should be small enough so that essentially you get a large number of tokens where also the many different comparisons actually give you additional information. So, and that's also like, if you want to use a transformer for your application, that's the first thing to think about. What is a token, right? So the dot products have to make sense, but you still want to have a large number of tokens, but not too many that computational complexity goes through the roof, right? Right. And here also an observation, right? If you train a transformer with standard ImageNet, you won't perform better than, so standard ImageNet, that's a standard data set in computer vision everyone works on. It's, I don't know, it's 100 gigabytes or 200 gigabytes, this order of magnitude. A transformer won't work better than a CNN. It typically works slightly worse. And that's one of our observations why transformers are for a big data regime. I do have examples where transformers work also in a small data regime, but generally speaking, a transformer, because it doesn't, for example, have the inductive biases of a CNN. A CNN is, in some sense, it has this translational structure. It assumes some things about the image a transformer doesn't assume. This helps it if you don't have too much data. It hurts it if you have enough data. Right. And essentially, so the vision transformer paper came out 2020, 2021, and essentially the last 2 years now, the majority of the computer vision papers also uses transformers as an architecture. Good. So these are attention maps, the different color, these are attention maps for computer vision. The different colors are now the different attention heads. And you see essentially what a transformer learns is semantic segmentation, right? But this is here is like with zebra here, and you see for the writing equipment here, it is very small detail, small feature. It's super hard to segment this out, and essentially, and the network isn't actually trained to do segmentation. It just learns that segmentation is a very useful thing to solve a lot of computer vision tasks. Right here, you also see you have the snow, so there's very little difference between all the different image parts. You have the road and the snow and the sea and the railguard here, and the network is able to very robustly segment these parts. Good. So, yeah, I wanted to show one example that goes more towards engineering applications. So that's some of my own work to show how that one can adopt transformers to the problems that are more of interest. So it's a very simple two-dimensional channel flow. So you have an inflow from the left, you have an obstacle, and here you see, it's not a very good visualization, I'm sorry for this. You see a small Van Karman street behind the flow. What you work with is vorticity. So we have a two-dimensional, so that's incompressible Navier-Stokes for the experts, knows the boundary conditions. So I computed vorticity just out of the flow because when I think once I have vorticity, I have a scalar field and I can just treat everything as an image problem. And here in the training data set, we actually varied the position and the shape of this obstacle a little bit to get some variability. And essentially what we do, we always look at some local patch in the flow, and we do the same thing as the vision transformer, right? We take essentially the grid points. So this is also finite element simulation, but it wouldn't matter if you took a finite difference simulation. So you have some grid points, regular elements. We took these elements. We always took, I think here this was 8 by 8 pixels or grid cells together. This formed the token now. And the difference to a vision transformer is, right, we do this now, we have multiple time steps. So, and the task we gave the network for training was, and these are actually, so we used to, so it's self-supervised. The task we created was to actually do forecasting or prediction or simulation. We asked the network to output the flow at the future time in some smallish region in the center of the flow. So these are the predictions. That didn't matter too much. We have got much better results now. The point I wanted to look at here, so we see that actually, so the yellow line is essentially the prediction. So we see overall, so yeah, right as a reference here, yellow, this is the prediction. We see that the network seems to do a decent job. If you look at the 1D plots, you still see it's not perfect, let's put it this way. But I really wanted to look at was really, again, the attention map, so the angles. So what information does the network actually use in the prediction? And, right, so what we really measure now is essentially the angle between these two small patches in the different feature spaces. And here's one example. So that's essentially our input. That's what we feed to the network in a tokenized fashion. So there are already quite a few tokens. So it's like about 200 to 300 tokens. And these are the attention maps here. And what you see here is that the network actually uses kind of a natural structure. So it also does some kind of segmentation in the flow between the low and high vorticity regions to actually solve the prediction problem we gave the network to do. And you also see this nicely if you look at the flow region where the obstacle is in the flow. You see that the network really uses mainly this obstacle to do the prediction, which is what you would expect, right? Like the obstacle, the boundary conditions where it drives all the flow behind the obstacle. And for those at least the fluid mechanics background, that's sounds very plausible and natural. And here's another example where you have kind of a wave going through the flow, and you can see the wave nicely in the attention map. So it shows us essentially how the network works a little bit internally. And that's a fairly simple adoption of a vision transformer model to this flow problem. Works pretty surprisingly well. This is also like that's a transformer with a few 100,000 parameters. So it's a really small transformer. It's a 2D simulation. We generated like 20 or 30 simulations with finite elements over. But to show, right, so transformers are really meant for a large data regime, but we also can work in a small data regime. I didn't do a comparison to a CNN. Probably would do a comparable job here. I do really like the attention maps as a way to understand what the network is doing. Yeah, and here maybe this transformer for the fluid flow problem, you can very nicely actually also translate it to a more classical simulation point of view, right? A token is now a small patch in our region, in our flow simulation, but it's very similar to a finite volume or discontinuous finite elements where like you would also take, yeah, you have these small cells, hard boundaries, and in some sense, if you want, we have learnable basis functions, but it's similar to these finite volume, finite element maps. Right, the attention, as I mentioned multiple times, it's an inner product. It's the central building block of all of scientific computing. So that's what we do all the time if we do something with Galerkin projection type. And I already mentioned that these feature spaces, you can think of it as a nonlinear generalized form of PCA or proper orthogonal decomposition. Good. Yeah, with this, I would come to the end of a transformer part. So one of the central motivations, and especially also in the context of RAISE, is, right, it's highly parallel training that scales to networks of billions of parameters. You know, the attention mechanism allows to model complex dependencies in the data, not only essentially, yeah, you have some input and essentially can use an arbitrary correlation between all the different input tokens. That's a little bit also the disadvantage of transformers, that you compute, you have a quadratic scaling in the number of tokens that puts in practice a limit on the number you can use. However, there's a lot of work in the last 2-3 years on essentially how to make sparse, right? So you get an attention matrix in the end. You compute, have a dot product between all pairs of vectors in it, and essentially how to use a sparse matrix for this. So between which tokens should you compute it with attention? And there's a whole, yeah, a few hundred papers on this. So people have looked into this. Some, there are also some, like for example, the Big Bird paper is one of the solutions I like, that I think was also very amendable to scientific computing, that more or less does essentially a multi-scale approach to this problem. Good. Right, and one thing that I think is also like important, that the transformer is really the standard model for natural language processing and computer vision again. So this unification has, I think, many advantages, especially if we combine it with self-supervised representation learning, that you essentially train a few models on very large amounts of data, and then you specialize these for different applications. Yeah. One thing maybe for scientific applications that are relevant, you can also use attention creatively. So I've seen very interesting approaches where essentially the attention mechanism wasn't really used like in the original transformer papers, but people thought, like in my domain, actually, I really want to measure somehow the correlation between these parts, and then you can also use it as part of other network architectures. For example, with graph neural networks, you can put it on top of it or just really use it somewhat on the input data. And last but not least, and that's, I think, very relevant for the applications in RAISE, it's really a generative predictive model that, for example, you can use for simulations to generate dense output. All right, good. I think I would say I do this part still, and then we probably should stop. So that's, I still have a part essentially on the work I'm doing on weather and climate, but
please go ahead. Yeah. So I think we started the training a little bit later, so it's not a problem. Thank you.
So this circles now back a little bit to the beginning, right? So as I said, I think in many domains in science, we have large amounts of data, and especially observational data, which from my point of view, makes the machine learning even more exciting and more interesting. But also the simulation output, right? Like with CMIP6, that's hundreds of petabytes from the big climate simulations. But if you do a DNS simulation for fluid flow, you also, it's no problem to generate many, many teras and petabytes if you want. But yeah, and you have this observational data, for example, from satellites, Earth observing satellites that look out into the universe, but also like particle physics is another field where you have large amounts of measurement observational data. One thing, okay, I think I missed the question. Maybe we can get back to it at the end. Yeah, one thing where I think neural networks make most sense is if you don't have complete knowledge of our system. So there's essentially, and Morris already mentioned it, there's this topic of emulators. You have a Navier-Stokes simulation. Navier-Stokes simulations are expensive, and you build a neural network that essentially is a faster solver to do what your FEM solver or Lattice-Boltzmann or whatever does. So that's one application, and it can be extremely useful for a lot of applications, right? But there's essentially this other side of things where we do not have a complete knowledge of our systems. That's the case for weather and climate, as I explained, right? Like with small scales, we don't have equations, we don't have an understanding. You have it in many complex interacting systems where our classical reductionist approach to science and engineering doesn't make sense or isn't really scalable. So that's something where that is important. And that goes back to a point I discussed already with Morris, that large neural networks actually learn statistical representations, right? So like if you do natural language processing, what is the correct translation for a word is essentially a probabilistic problem. You can essentially use context to give one possible answer, but there are often multiple words that would be plausible translations. And sometimes also the context might not be enough to completely disambiguate the translation you want to make. And this is also something I think that is very interesting for science and engineering, because this is exactly, again, where our classical models are not very good at. If you have we can do one fluid simulation, but essentially once you want to take the uncertainty in your inputs into account, you do ensemble simulations, which are very expensive, or stochastic PDEs, which are even more expensive. So, and this is something I think where neural networks are known to be very good at to deal with some uncertainty and ambiguity. And I think that's also an aspect that hasn't been explored. And that's, again, it works best if you are essentially with large data regimes, with large networks. If you do representation learning, that the network just sees many, many different examples, many possible answers for different tasks and translations. But that's just Jan LeCun made the point recently that here, like if you look at just this outline, there are just many different answers what to pose of this person here, right? So it can be a backward-looking dancer or forward-looking dancer, and yeah. But neural networks are just a tool that can deal with it in contrast to our classical reductionist approaches. Yeah. And I think that's something that just applies to weather and climate, but also to many other systems. Good. I would essentially a little bit stop here simply because the next part, that's the project I'm working on doing representation learning for weather and climate. The point here is that we have large amounts of observations and we 6 petabytes of data. And we essentially try to demonstrate that with large-scale representation learning that is standard now in natural language processing and in computer vision, you can carry this over to scientific applications. And there are many important applications we care about, like weather forecasting and climate projections, but also like downscaling, so creating higher resolution data or understand impact analysis. And the one thing that is really exciting for me about this project is that this question, can we actually use these networks, for example, that essentially digested 6 petabytes of observational data? Can we use it to understand or to answer scientific questions? So, and this is something, right? It doesn't really make sense in computer vision and natural language processing. People looked into these large neural networks and you can see the grammar in there, but we kind of completely understand the grammar of human languages. And here the question, for example, in the atmosphere is, can we understand long-range interactions in the atmosphere, which we really cannot get out of the partial differential equations because we are very local in space and time. And so that's something I'm very excited about. If like, yeah, can you actually use these big networks to do science and not just to solve applications? Of the applications, if we could do better climate projections, this would be a huge thing. Good. Yeah, be essentially working on this. I will here just scroll through because yeah, it would take a bit long to go through it now. We essentially have adapted a transformer architecture for the specific task. We defined what a token is. And we build a transformer that I think fits very well for our specific purposes. But this would take us too long. So almost there. Right, good. So that's the point I already made. Transformers are forecasting, prediction, simulation models. So that's something I really would like to see explored. And I unfortunately think I don't have enough time to do all of this myself. And this is a lot of similarity to time-stepping methods. A last point, maybe I want to put out this relationship between physics and learning. Right? Maybe also a bit maybe it's a bit controversial, but I would like to put it out. So in scientific machine learning, right, we often think that you should put in the constraints from physical models, the symmetries, energy conservation into a machine learning model. And for me, that's really like a very interesting, but a very open question if you really should do this. The part is these hard constraints typically severely degrade the efficiency of a machine learning. And are there maybe better ways to enforce physical constraints, or should we really enforce it? Like if you train on enough data, will the network just learn energy conservation? Will it learn momentum conservation? So that's something, yeah, I would like to maybe see explored in the future. So that's right on the left-hand side is in some sense, we do have a classical model. And then a second part that I think is, as I mentioned, very interesting is really this going to observational data where we don't know the equation. So can we really leverage essentially this observational data, and is machine learning maybe a good tool to really leverage these tools? Yeah, so are your neural networks really, and that's really the reductionist models, right? How we build equations. We ignore these higher order effects that are messy to write down equations, but weather and climate is one good example where we just seem to drive a lot of uncertainty in our current simulations. And as I said, also, can we maybe use this to provide a new understanding of physics? Good. So in summary, I think self-supervised representation learning, so learning on large amounts of data to have domain-specific but task-independent models has great potential for science and engineering, and it's completely untapped. We do have, not everywhere, but in many cases, we do have large amounts of unlabeled data, both from simulations and from observations. And it just provides a means to make use of this data. And also this idea of having a domain-specific but task-independent model actually fits very well the way how we typically do science, right? Like we develop an equation to describe a certain phenomenon that we can use for forecasting, for stability analysis, that we typically don't just do it for a specific application. And transformers are an architecture that fits very well with representation learning, but you can also just use it on labeled data, works also very well. It has proven to be very versatile and very powerful, and it works for a lot of different things. You just have to think about how to define a token so that these dot products make sense. Largely unexplored for science and engineering. Just this year, the first papers came out, right, which is 6 years after the original transformer paper. And I just think also it fits very naturally with our overall scientific computing framework, because it just consists of things we kind of are used to: transformations between feature spaces, computing correlations between some kind of embedding of our data. Good. With this, I would like to thank you for your attention. And yeah, so there was one question in the chat which I overlooked. So let me try to find it again. And if there are any more questions, I'm happy to answer them. Right, so there's the question: what happens if you overlap with small regions tokens? This was, yes, it's a very interesting question and very meaningful and relevant. In the original vision transformer paper, we didn't overlap it. if you come from more basis representation point of view, yes, you would assume you should overlap them a little bit. Nobody has looked at it, and I didn't have the time yet to do it. So it would be very worthwhile to try it out. I think for simulation problems, yes, this seems to be very clear.
Bit like the slide we had a little bit in CNNs also, right? But yeah, other questions. Thank you first of all, Christian, for a very interesting talk. I mean, before we forget this, it was really insightful, especially looking in the representation for getting future findings in science and in the different hats. I think that has quite some potential. If we maybe not as humans are too biased to look at, we already know. So, and that brings it also to RAISE a bit, because we have some tasks that also want to do physics-informed machine learning. But on the other hand, of course, as you said, it introduces a bias of things we already know instead of finding new stuff, maybe. That's basically otherwise very constrained. But yeah, we have maybe a little bit more time for questions. If someone else has any question, please shoot. Don't see a hand right now, but please feel free to also unmute yourself. We are not so many participants, so should be okay.
I assume it was a lot of information in a short amount of time. So if any other questions come up, feel free to just send me an email or get in touch otherwise.
Sure. Or we maybe make another training on the outcomes of AtmoRep. It would be probably also something interesting to see. That's a German project, you said, or it's a
that's a project together with Martin Schulz from JSC.
Okay.
Might be a familiar name, and Ilaria Luise from CERN, and Michael Sonnewald from Princeton GFDL, and Anish from Boulder, Colorado. So it's an international project where we really try to do is proof of concept that representation learning can work for scientific applications. It's really made possible because there's this very nice data set here with ER5 analysis that is essentially super nice for machine learning. It's just 6 petabytes of essentially scientifically validated data you can just download and machine learn on.
No, highly interesting. So I think that's really good for science, especially as you also put it out. Many of the applications are always natural language processing, and now this really puts it a bit more into our field and RAISE. Also, the work on the fluid flow was, I think, also very interesting, that there are applications.
Yeah,
but yeah,
I think it's really with the natural language processing, right? Natural language processing is a temporal model, right? So this puts it immediately somewhat close to all the science applications, or at least all the PDE, ODE stuff that you do have a time dimension. So that's always how I think. If I see something in natural language processing, right, I always think of time evolution. We can adopt it to time evolution. So, and with a vision transformer, right, this covers essentially the spatial domain. And so I think that's fairly general now applicable to science and engineering.
Indeed. Good, but yeah, I don't know if you had more questions, going once, perhaps twice. If that's not the case, I would close maybe with a couple of slides here. Again, thanking Christian, basically also for his availability on a very short notice, I have to say. Thanks for this. I just wanted to basically also say thanks for the audience, not to make it here very long. Thanks for joining us. As you know, if you want to have more information about RAISE, you have our website. Get in touch with us, especially if you want to think about adopting the CoE RAISE framework, which I think has now lots of time saving for people that go to different EuroHPC resources, to different HPC resources in Europe in general. So there, please contact that if you want to know how the technology is scaling, or basically how you deploy the different modules. We have job scripts there for many of the different systems and for many of the frameworks, including now new popular things like deep speed, for instance, or hyperparameter tuning with RayTune. Of course, here goes the advertising. Our YouTube channel is there for you. We have done lots of seminars and trainings in the last year on hyperparameter tuning, as I was just saying, on some of the components, but also on AI models. So we had something on autoencoders, for instance. So please feel free to have a look at YouTube. This video here will be also part of the YouTube channel very shortly. So it maybe makes sense to subscribe to our channel. Today, we had the transformer models, and I think we will see more in RAISE about this. I think we have a very exciting talk from Christian, really motivating us to adopting this. And we will hopefully maybe in a year from now having also maybe some transformer models adopted in the project where we can do some training on. In the next month, There will be hopefully a training we're working on this, on surrogate modeling, perhaps not directly fueled by transformers yet, although they could partly do the job as we hear. This is basically on other approaches. For instance, here you see some for wind farm layout from BSC at Barcelona Supercomputing Center, but there will be also some other basically sciences in context, and of course a proper introduction to surrogate modeling from a certain degree and how it can benefit from HPC. That's all I wanted to leave here on the table for you. Thank you very much, everyone, for joining us today for the Transformers. Also, again, thanks for Christian for your availability, and see you next time.